Welcome to Dimensional Analysis and Modeling. Welcome to one of the most practical topics in fluid mechanics, dimensional analysis and modeling. This chapter is all about simplifying complex problems. Rather than relying on lengthy equations, you'll learn to work with dimensionless numbers to predict and scale fluid behavior. Why does this matter? Because every major engineering breakthrough, from wind tunnel testing to hydraulic models, relies on these principles. You'll see how to convert real-world problems into manageable experiments. By the end of this chapter, you won't just memorize formulas, you'll understand how to think like an engineer. 1. Understand dimensions and units clearly. Before we get into formulas, it's crucial to understand what we're actually measuring. Dimensions describe what you're measuring without numbers, like length, mass, or time. Units, on the other hand, give dimensions a number, like meters or seconds. Focus on the 7 primary dimensions: mass, length, time, temperature, electric current, light, and amount of matter, N. Everything else, like force or energy, is built from these. Why is this important? Because dimensional consistency keeps your equations valid. You'll also learn how derived dimensions simplify your work and prevent calculation mistakes. 2. Always check dimensional homogeneity. Every valid equation in engineering must follow one golden rule: dimensional homogeneity. This means every term in your equation must share the same dimensions, no exceptions. Why does this matter? It's your built-in error checker. When your dimensions don't match, your equation is physically meaningless. You'll use this for 3 key purposes. A. Catching mistakes early through error checking. B. Simplifying equations by converting them into dimensionless forms. And C. Discovering hidden functional relationships that make complex problems easier to solve. Mastering this principle will sharpen both your calculations and your engineering intuition. 3. Make equations simpler with non-dimensionalization. Equations get easier to understand when you convert them into dimensionless forms. This technique removes the clutter of units and focuses only on the relationships that matter. Why should you care? Because non-dimensionalization helps you compare different experiments, scale models, and real-life systems without needing complicated recalculations. The secret tools are these key dimensionless numbers: Reynolds number, Re, inertia versus viscosity; Froude number, Fr, inertia versus gravity; Mach number, Ma, flow speed versus sound speed; Euler number, Eu, pressure versus inertia. Learning to think in dimensionless terms is a skill every great engineer masters. 4. Simplify problems using dimensional analysis and similarity. Dimensional analysis is a game changer. It reduces the number of variables you need to consider, making complex problems easier to solve. This approach is especially useful for designing experiments and comparing results from models and prototypes. But how do you make sure your model represents reality? Through similarity conditions. A. Geometric similarity. Keep the shape the same, just scale the size. B. Kinematic similarity. Ensure velocity patterns match between model and prototype. C. Dynamic similarity. Balance the forces so the ratio stays the same. Master these concepts and you'll be able to predict real-world performance using small-scale experiments. 5. Master dimensional analysis with repeating variables. Dimensional analysis becomes systematic with the Buckingham Pi Theorem. It tells you how many dimensionless groups you need. Just subtract the number of primary dimensions from your total variables. Follow these simple steps. First, list all the parameters involved. Next, write down their primary dimensions. Calculate how many pi groups you need. K equals n minus j. Choose repeating variables carefully. Avoid dependent ones. Build your dimensionless groups by forcing combinations to cancel out dimensions. Finally, write the clean, dimensionless relationship. This method turns messy problems into elegant, universal equations. 6. Focus on the most useful dimensionless numbers. Dimensionless numbers simplify engineering by comparing forces and effects without worrying about units. Think of them as shortcuts to understanding complex systems. Start with the essentials. Reynolds number, Re. Inertia versus viscosity, used everywhere in flow analysis. Froude number, Fr. Inertia versus gravity, essential for open channel flows. Mach number, Ma. Inertia versus compressibility, key in aerodynamics. Prandtl number, Pr. Momentum versus thermal diffusivity, important in heat transfer. Nusselt number, Nu. Convective versus conductive heat transfer. Weber number, We. Inertia versus surface tension, great for droplet studies. And Euler number, Eu. Pressure versus dynamic pressure. By mastering these numbers, you'll quickly identify the dominant forces in any problem. 7. Make experiments meaningful with similarity rules. Not all experiments are created equal. Similarity is what makes a small model predict real-world behavior. With complete similarity, all dimensionless groups match perfectly between model and prototype. But in reality, we often settle for incomplete similarity, where some differences are unavoidable. A great example is wind tunnel testing, widely used for cars, planes, and buildings. To get accurate results, you must match key dimensionless numbers, especially Reynolds number for flow behavior and Mach number for compressibility effects. Without proper similarity, your tests could lead you in the wrong direction, so always check your scaling. 8. Don't worry about perfection. Understand incomplete similarity. Full dynamic similarity isn't always possible, especially in real-world experiments. That's completely normal in engineering practice. For example, free surface flows, like ship models, focus on matching the Froude number instead of the Reynolds number because gravity effects dominate. In wind tunnel or water tunnel experiments, you often have to extrapolate results when matching every dimensionless group is impossible. The key takeaway? Don't aim for perfection. Understand the limitations and adjust your experiments accordingly. Engineers thrive by making smart approximations. 9. See dimensional analysis in action across industries. Dimensional analysis is not just theory, it powers real-world engineering solutions. In energy systems, it helps design better turbines and pumps by simplifying flow behavior. In aerodynamics, wind tunnels rely on similarity analysis to predict how planes and cars will perform. In biomedical engineering, doctors use Reynolds and Froude numbers to understand blood flow and design medical devices. In weather modeling, scientists scale up small-scale experiments to predict global weather patterns using dimensionless numbers. Mastering this tool gives you cross-industry versatility. Think like an engineer no matter where you work. 10. Simplify and solve smarter with dimensional analysis. Let's wrap up with the essentials you must remember from this chapter. Dimensional analysis cuts through complexity by reducing variables and simplifying problems. Similarity principles let you replace expensive full-scale tests with smart model testing. Dimensionless numbers like Reynolds, Froude, and Mach numbers reveal hidden patterns in fluid behavior. Buckingham Pi Theorem gives you a reliable, structured method to derive these dimensionless groups. Incomplete similarity? No problem. Engineers use extrapolation and correction techniques to make accurate predictions. With these tools, you'll solve problems faster and smarter.